Now we're going to have more examples on the derivatives of natural logarithms. But before we can proceed to our problem sets today, you need to remember your natural logarithmic expansion, which is pretty similar to your logarithmic expansion. The only difference is that we're using ln. So we're still using the three logarithmic expansions that we had before, and we're also using the formula for the derivative of ln x, which is 1 over x. So let's have our first example. Now, the examples that we're going to be working on today will be a little bit more complicated than the previous examples that we did in our lessons of logarithm. The reason why it's going to be more complicated is, one, it's using, or you need to use logarithmic expansion, and also you need to use the rule in derivative and the rest of the rules that we have learned before. So in this function, we need to find the derivative of ln of x plus 1 all over the square root of x minus 2. Now, one technique that you need to remember in finding the derivative of logarithm is that don't think of product rule or quotient rule right away. You need to first think of the logarithmic expansion before you can proceed to your derivative rule. And that's what I'm going to do in this example. Because if I use the quotient rule in finding the derivative of this function, I'll still be able to find the derivative of the natural logarithm, but it's going to take me so much space because of how complex your fraction is. So what I'm going to do is I'm going to expand my natural logarithm using the expansion that we had before. So if we have ln of a over b, it's simply ln of a minus ln of b. So that's still your function, but I just expanded it using the logarithmic expansion. So now I'm going to find the derivative of my first function and then my second function. So for my first function, this one will be a lot easier because the derivative of ln of x is simply 1 over x du dx. And for this one, I'm going to use the chain rule to find the derivative of x minus 2 raised to 1/2. So f prime of x is equal to the derivative of ln of x plus 1 minus what I did for the second function is I used my expansion again by getting rid of my exponent and multiplying it with my natural logarithm. So since this is just a constant, I can just set it aside and just deal with it later so that I can concentrate on ln of x minus 2. So all I have to do is to get the derivative of this function and set aside my constant. So that's for my second term. So for my derivative, the derivative of ln of x plus 1 with u equals x plus 1 and the derivative of u, which is 1, my derivative for my first function, or my first term, will be 1 over x plus 1 times 1. And my derivative for my second function will be 1 over x minus 2 times 1, because that's your du. And don't forget that you still have your constant 1/2 from the exponent or expansion that we did a while ago. So we have 1/2 times 1 over x minus 2 times 1. Now this will be acceptable since you performed logarithmic expansion and you also performed the derivative rule for logarithm. However, if you still want to simplify your function, we can have the first function as 1 over x plus 1 minus 1 over 2 times x minus 2. And this is our derivative. Now in this second example, we're using implicit differentiation because we are finding the derivative of y in terms of x. So it's going to be a little bit more complicated than example number 1 because of the many rules that we're going to use in this example. So the first step that we're going to be using is multiplying my right-hand side and my left-hand side by ln. And by doing that, I'll be able to set my exponent right down here by expanding it using the power rule or the power expansion from natural logarithm. So I have ln times 1, which is ln of y, and we have ln of x sine x by multiplying ln to my right-hand side. And we know that since we have a natural logarithm here, we can still expand this function into x sine x or sine x times ln of x. So now we're deriving the first set and then the second set. So the derivative of ln of y which uses the implicit differentiation, will simply be 1 over y. But since you're finding the derivative in terms of x, you will write dy over dx, or y prime if you want to use y prime instead. Now, for this function right here, I'm going to use the product rule. Now, going back to the previous example, wherein I also used this type of expansion, when I use that type of expansion, I only set aside that exponent. The reason why I set aside 1/2 is because it's a constant. But this time, it's no longer a constant, it's sine x. It's a totally different function, so you can just multiply them together, which uses the product rule in deriving the natural logarithm. So now you have the derivative of sine x times ln x with respect to x. And by using the product rule, I'm going to show you all the steps in this one right here. So copy your f of x times the derivative of g of x plus the derivative of f of x times g of x. And to further simplify your derivative, 1 over y dy dx will just remain as 1 over y dy dx because we cannot simplify this any further. And sine x, we copy sine x. The derivative of ln x is 1 over x. The derivative of sine x is cosine x, and you copy ln x. Now this is just the first half of our solution, because dy dx is still with 1 over y. So what we need to do is to get rid of 1 over y with your dy dx to have your derivative for this function. And that's what we're going to do on the next slide. We're going to get rid of 1 over y. And to get rid of 1 over y, we know that all we have to do is to multiply this side of your equation by y and this whole side of your equation by y as well. So that's what I'm going to show you on the next slide. So once again, we need to remember that we're finding the derivative of the function in terms of x for y equals x sine x. This is your left-hand side from the previous slide, 1 over y dy dx, and this will be your right-hand side. Now, since we're multiplying both sides by y because we want to get rid of 1 over y in your dy dx, we're able to achieve that by multiplying them by the function y. However, since there's nothing to multiply y with or simplify y with on this side of the equation, the only option is to distribute y to the second term and the first term, but we're not going to do that. All we have to do is just copy this entire term right here, and this y right here will still be y. However, we know that y is equal to x sine x. So what we're going to do is to replace y by x sine x so we can complete our derivatives in terms of x. So dy over dx is equal to the quantity of sine x over x plus cosine x ln x times x sine x.